Good evening, everyone. It's with great pleasure that I'm able to welcome Virginia Fratello to Waterloo Architecture as our lecturer this evening. Virginia is an architect, a designer, an educator. She's a graduate of Columbia University, where she received her Master of Architecture degree. And she's the principal of Emerging Objects, an experimental design studio that's based in San Francisco with her partner Ron Rael. And she's also a professor of design at San Jose State University. Emerging Objects is one of the 5 studios that was part of the Materials Matters exhibition in the Design at Riverside Gallery. And of course, Virginia's work, one of the highlights of the show, the Salty Glue piece, was done by Virginia and Emerging Objects. The incredibly unique piece that was 3D printed using salt that was locally harvested in the Bay Area. Emerging Objects, they refer to themselves as an independent, creatively driven 3D printing make tank that specializes in innovations using rapid prototyping technologies to generate new architectural building materials, components, and assemblies. And I think one of the things that's really interesting about the work is the kind of directed research at a particular scale that's not just looking at the kind of formal spatial design of spaces, but looking at the objects and component parts that make up that space and how they come together, but also looking at the way in which new technologies link up to materials and perhaps the making of those materials. And they talk about 3D printing, or I've heard Virginia sort of ask the question, can we 3D print buildings? Can we think about these new technologies not just as model making tools or representational tools or even prototyping tools, but could we think of them as sort of larger devices to make architecture? And they say not as thinking of 3D printing of buildings, not as a kind of futuristic proposition, but as a serious question to which their work and their studio is looking for specific answers. And they do this perhaps by recreating the fundamental components of architecture, the 3D printed brick, and by operating as experimental cooks that develop material recipes alongside the generation of formally and spatially compelling components and structures. Besides being highly innovative on the side of materials and technologies, from a design perspective, I'm always fascinated with their work because it is so compellingly beautiful, sort of image after image. And I think that it's not just about sort of thinking what the material artifact is, but about, what we can do with the technologies themselves. Rael Fratello has been the recipient of many awards, including the AIA's Emerging Voices Award and Metropolis Magazine's Next Generation Design Award. They were also finalists for the WPA2 design competition and winner of the Van Allen Institute's Life at the Speed of Rail competition. The work of the firm has been published and exhibited in numerous national and international venues, and I was really excited that we were able to include them as part of the show in our gallery. And certainly for those who are interested in material explorations, Virginia's talk this evening, Full-Scale Study Models, focused on the designing and making of prototypes, should be especially compelling. Please join me in welcoming Virginia Fratello.
Thank you so much, Isla. Thank you all for coming. It's always an honor to have the opportunity to share your work with others. And I hope that this inspires you as you go back to your studios tonight or maybe tomorrow and continue working. I'm going to show 3D printing, but I'm also going to show some other projects developed by Emerging Objects and Rael Fratello as well. We are a small studio in Oakland, California, and the focus of our work is very heavily material-based. And we are I think, deeply invested in very traditional materials, in agrarian materials like straw and hay and mud, which you see here. And we're interested in using those materials in our work and thinking about how we can use them in the 21st century in an urban context and with industrialized materials as well. We have experimented with what we unnatural materials, and these are the materials that we've developed for 3D printing. They're traditional architectural materials like concrete and wood, but we use them in very unnatural ways. And then we're also interested in what I call kind of a neo-vernacular material, which for the Bay Area, you might consider a vernacular material something like a redwood tree or redwood. But a neo-vernacular material might be a circuit board, for example. So we use these materials in full-scale study models to provoke conversations around social and environmental and political issues, and to think about how these full-scale study models might be precursors or prototypes for buildings at some point in the future. So it's important to know that Ron and I both come from very rural places. Ron grew up on a cattle ranch in Colorado, stacking hay bales, and I grew up on a farm in North Carolina, picking, topping, and burning tobacco every summer. So what you bring to your architectural education is as important as what you take away from it. We still have a very strong connection to those materials. This is one of the first projects that we did when we started working together. It was a design for the hay bale house, and we entered it into the SECA home house competition, and we were one of 10 winners, and they were fully intending to build the house, but it was never built. The design is for a concrete structure, which you can see here, that housed stairs and kitchens and bathrooms that would anticipate the arrival of hay from the fields that would be stacked around it over the fall. And so the house would become insulated and snug and warm and cozy, and we would allow, over the course of the winter, the cattle to eat away at the house, so that in the summer the house was naked and cool again. So this was kind of a first foray into thinking about agricultural materials and industrial materials coming together. After that, we were invited to propose a design for a hotel room on top of Queen Elizabeth's Hall in London, which would be a 6-month temporary installation. And you had to be able to carry all the materials up in the elevator. So we said, well, let's build this out of straw bale again, and we'll pop in these glass inserts that house the programmatic aspects of the building. But they decided not to build it either. We did finally get to build this maze out of straw, though, which was fun. So we put all of this on our website, and it's really important to put your work out there so people can see it. And a gallery in San Francisco called Hedge called us, and they said, we really like your straw and your hay projects. Will you build a building out of straw for us? So finally, we said, yes, we can build something. So we were asked by Hedge to build their gallery installation for the SF MoMA 2021 festival at Fort Mason in San Francisco. And we stacked up straw bales from nearby Concord into this exhibition space where they were displaying the objects of art and design within this large warehouse venue. And we had a truckload of straw bales delivered to the site so they could be assembled pretty quickly in one day. And we designed these metal insertions that would weave through the double width of the straw bale. And these metal elements are sometimes lintels over the door. They frame openings so you can see in and out. They are the spaces where objects are displayed. They sit on them like shelves. But more importantly, they structurally tie everything together. And in lieu of traditional plans and sections and elevations, we made this series of drawings so that we would all know exactly where each straw bale went and when to insert the metal elements. So the interior is very soft and aromatic, and because of the nature of the straw bales, it's very quiet inside this space. And this is a venue that has over 5,000 people come over a series of evenings. So when people came into this and it was so quiet and they could look at the art and they could smell the straw, they were really surprised to be in this space at this large event. The floor is the original flooring of the warehouse. If you look beyond, you see the white carpet that was laid down on top of it for all the other exhibitors. And we used another very humble, simple material for the ceiling. It's a window screen mesh, which is about $16 a roll, which did kind of a beautiful job of closing it up and allowing for some specularity of light to come into the space. And we designed and located the doors and the windows in such a way that you could never see all the way in to the interior of the gallery. You actually had to come in if you wanted to know what was inside, in contrast to the other exhibitors where you can see they had everything out on display, or they only built 3 walls. So you could walk down the corridor and see it, and there was never a reason to go inside and be with it. And at the end of the show, there was a line of dumpsters where all of this carpet and the sheetrock was thrown into the trash. But we loaded up the straw bales and we sent them back to Concord, where they became bedding for animals. And the steel shelves and lintels became shelves in the permanent gallery in San Francisco. So nothing was wasted. Sukkah of the Signs. This is AKA the Homeless House. This is a competition that we won in New York several years ago for the first Sukkah City competition. And if you don't know what a sukkah is, it's a temporary dwelling that was built to commemorate the 40 years of wandering that the Jews experienced in their exodus from Egypt. And it's built, I think, for 7 days over the Jewish holiday of Sukkot. So God has given many laws for building a sukkah, just a few of which are that a sukkah must be at least 10 handbreadths tall. It can be built on a wagon. The roof cannot be made of utensils, and the roof must be made of something that once grew in the ground. So there are many of these, and in thinking about the design of the sukkah, we certainly had to adhere to these rules, but we also wanted to address contemporary issues of homelessness as we talked about this project. And we had been collecting signs from homeless persons over the years and thought this would be a good opportunity to use those signs in our proposal for the homeless house, or the Sukkah of the Signs. And our proposal was to make this tall 20-foot structure that would just be made of simple 2x4s and clad with the signs that we had collected. And the furniture on the interior would be made out of recycled cardboard bales. And we were inspired by a mosque, a Somalian mosque in a refugee camp that we had seen in Yemen the year before. And the beautiful interior of this mosque, as the light passed through the holes and the handles in the cardboard material. And we thought, wouldn't this be a really moving space for people to come to in New York to think about this issue of homelessness, which is so prevalent in the United States. And we won. So we were invited to build our sukkah in Union Square, but there was one contingency. The New York City building code superseded God's building codes, and we had to reduce the height of the building from 20 feet to 10 feet. So the first thing we did was just squish it down to 10 feet. And this is kind of indicative of the way we all work together in our office, is to draw something full scale on the wall. And we decided it wasn't nearly as impactful and we didn't like this. So we decided to turn it on its side so it would be more like Noah's Ark or a Sandwalker from Star Wars. And then, of course, we had to collect more signs because we didn't have nearly enough. So every day during rush hour, we would go out into San Francisco. We went to LA. We had former students in San Diego collecting signs for us. And we met a lot of really interesting people that we never would have met otherwise. We met people who had really great senses of humor. We met people who, like this young woman, had flown her signs all the way from New York and told us about her secret stash of signs in Golden Gate Park, said we could have them, so we went on this scavenger hunt through the park finding them. We created a kind of false economy for signs because we would buy signs and then come back and the person would want to sell this sign again. And we were always amazed where these signs come from. So here, it's kind of this beautifully drawn help, right? I'm hungry, I don't have enough food. And it's on the back of a cereal box, which to me represents kind of America's industrial food commercialization, and food is an industrial commodity. And someone is using this to say, I'm hungry, right? I need help. The sukkah was built in Gowanus in Brooklyn. This is it. They were all built there, all 10 of them. So this is it coming out of the space and being loaded up on a big rig to travel in a parade with the other sukkahs across the Brooklyn Bridge into Manhattan's Union Square at midnight. So everything had to be set up between midnight and 3 o'clock in the morning so that on the first day of the holiday of Sukkot, everyone, hundreds of thousands of New Yorkers, could come see the sukkahs. Now, if you've ever been to Union Square in New York, you might know that there is a small homeless population living there. And pretty early on, this young man came up and he started yelling at people and telling them, don't look at this, don't believe this isn't real, these people are just artists. And we talked to him, we pulled him aside, and we said, we didn't make these signs. We used the money from the competition to buy the signs, so the money did go back to the homeless people who made them. And we've also convinced the organizers of the competition to auction off all 10 sukkahs and give the money to a homeless shelter in New York. And he turned around and he said, support the sukkah of the signs. And he became our ambassador for the whole week. This is a view looking up 9th Avenue of what once grew in the ground but is no longer connected to the ground roof. And of course, we always wanted people to read the signs and look at the surface of the sukkah, but also to look into it and through it and beyond and back out at the city. And I always like this sign because it reminds me that any of us can be homeless. We might not be suffering financially, or you might not have mental instabilities, but something like a natural disaster could make you homeless. So remember to be empathetic. And some people have compared the surface of the sukkah of the sign, where people write their deepest needs and their desires and their wishes, to the Wailing Wall in Jerusalem, which is another kind of stacked or aggregated surface that has people's deepest wishes and needs and desires written on pieces of paper and tucked into the crevices and the cracks in between the walls. in between the blocks in the wall. Okay, emerging objects. So emerging objects is a project of Rail San Fratello, at least that's how it started. It has probably actually superseded Rail San Fratello in its ambition. And it's become a corporation, and it's a tech startup in the Bay Area. It's a project that became a company that began by asking a simple question. Can strong and inexpensive building components be produced using 3D printing? What do? Well, we've created inexpensive structural materials for powder-based 3D printing, specifically for architecture, and we're developing methods to produce large-scale architectural assemblies using 3D printed building blocks. This is an example of the type of powder printer that we use. So this is all sort of under the umbrella of additive manufacturing, but 3D printing is actually the powder-based method of additive manufacturing. So this is a Z-Corp 350, 3D Systems 350. So on the left, you have the supply and the build bed, and on the right, you have a depowderer. And if you're not familiar with how this process works, there is a supply bed and a build bed. And on the powder supply side, there's a powder spreading roller that rolls a very thin layer of powder across to the build side, and then an inkjet head, literally an HP inkjet head, the same one in your inkjet printer, sprays binder onto the surface of that powder in a cross-section of the three-dimensional model that you've made. And then that build bed drops down, the supply bed lifts up, and the powder spreading roller spreads another thin layer of powder. And this happens again and again until a three-dimensional object is built up. And this is an example of something very typical that you could build on a 3D Systems printer with a 3D Systems proprietary material, which is a plaster-based material that's white, that is essentially material-less in its whiteness. But you can see it has a lot of detail and a pretty high resolution. And this is an example of someone modeling something three-dimensionally in the computer, which I'm sure all of the students here are familiar with. The print head spraying the binder onto the powder, and then that part being excavated from the powder itself and then brushed off. So that's how it works. So at Emerging Objects, we create materials that are sustainable. So the United States Department of Energy estimates that 3D printing uses 50 to 90% less energy than traditional methods of manufacture. And we're also interested in using materials that are in the waste stream, so things that are going to landfill that could instead be recycled. We create materials that are durable, so we're developing cements that crystallize, and they have strength. They're stronger than Z Corp's proprietary materials. And we're also interested in using them at architectural scales, so they have to be affordable, because a bucket of 3D Systems powder costs $1,200. So that's a bucket, right? But I can get a bucket of salt for $11. So there's a big price difference, right? So what if we could 3D print architecture? Well, since 1996, people have been trying to 3D print architecture at a very large scale, starting with Barak Khrushchevnis at the University of Southern California. And here we are now at 2015, and you can see the exponential increase in inventions, including machines and materials for architectural applications that's happening, most of which is in California and Northern Europe, I think the Netherlands. And Emerging Objects shows up on this timeline 5 times, actually starting with our planter brick, which was Rails and Fratello, so it was even before Emerging Objects. But in order to do this, we've had to hack our machines. And we started hacking them with the ground beneath our feet. Sand. Sand was the first material that we decided to deploy in the 3D printer. It's one of the most ubiquitous materials in the world. It's mined in almost every country. And we decided to 3D print in sand for an exhibit called the Biennial of the Americas in Denver, Colorado in 2010. And it was an exhibit called The Nature of Things, where artists and architects were asked to look at the relationship between themselves and the built environment. And we decided to project a future scenario where computer-aided design and computer-aided manufacturing would lead to buildings where the material source and the building material itself were seamless. And we wanted to present these 3D printed study models as if they were scale models for buildings, and we included people in them. And we challenged ourselves to make forms that could not be made any other way. And we experimented with adding other materials to the stand, such as these fibers, which is why this is very furry. And And there was a point when we realized we were limited by the dimensions of the build bed of the 3D printer, which are 8 inches by 8 inches by 10 inches. And everything we were making to go on the table was that size. And we finally realized, oh, we can stack things up. We can go vertical and we can go horizontal if we start thinking about how things interlock and connect. And we had a real breakthrough moment here where we decided this did not have to represent something larger. It wasn't a model of something else, but that in fact it could stand alone as a 3D printed, mass customized concrete masonry unit wall. And this is the moment when we realized, oh, let's make 3D printed bricks and tiles using our materials so that we can make architecture. And we've continued to explore that. This is also 3D printed sand. And in this case, you can see the 4 blocks. They're each 12 inches by 12 inches by 6 inches. And on the other side, we're actually exploring how the block itself, the boundary of the block, can be dissolved so that it reads as a continuous surface. The involute wall is made out of 3D printed sand. And this is an exploration in thinking about sound attenuation, what other sorts of performance-based criteria you could have within these complex geometries that we now have the capability to print. And the quake column, also 3D printed out of sand and inspired by Incan masonry. So when there's an earthquake, because of all the unique and various interlocking moments in these bricks, or these stones, I should say, they dance and they bounce, but then they settle back into place and the wall doesn't fall over. So we wondered if we could explore that same technique here, because we could 3D print blocks that also had unique interlocking moments. Every brick didn't need to be the same. And they could be stacked up to create a kind of modern interpretation of this wall that would still have some earthquake resistance to it as well. And each of these blocks is numerically coded, and if you look at the top, you can see each block has a handle, so you can insert your arm in it, because they're quite heavy, in order to lift them to put one on top of the other. And we did a simulation of an earthquake in the computer, and it did work, but we did not put it on a shake table. That's yet to come. So from sand, we moved on to clay. This is one of mankind's oldest building materials, now in its 30,000th year. How can we go from this to this in clay? And we experimented with 3D printed ball clays, with porcelains, bisque firing, and glazing. And we thought, could we begin to rethink the traditional brick? So here, for example, is a new brick that has the same dimensions as a common brick, but it has these different openings in it that allow for plants and vegetation and water to sit in the wall, so that we could make a masonry wall that could be green and help affect the microclimate of the building and the surrounding area. We've also looked at other very traditional methods of using clay in architecture. Here in the Muscatese window, evaporative cooling properties are taken advantage of when hot air passes through this wooden screen and over the surface of the clay pot that's filled with water. The air turns cool as it moves into the interior and pushes up the hot air, which is vented out the roof. So how can we take something very traditional, beautiful, and simple and rethink it for the 21st century in additive manufacturing? We designed what we call the cool brick, which, when it gets wet, warm air passes through the brick. Because of the lattice structure of the brick, there's increased surface area, and that air becomes cool as the moisture is released from the ceramic and as it would move into the interior, the air would be cool. So this brick operates at 2 scales, kind of the macro and the micro. Because the lattice exponentially increases the surface area, there's more cool moisture in the air, but also the 3D printed clay itself has lots of air pockets in it. So all of that increased surface area contributes to the success of this. When you 3D print with clay and you fire it, it shrinks. And it doesn't always shrink the same percentage, and it doesn't always shrink in the same dimension. So when we were stacking the bricks, after they had been disc fired, of course, they didn't go together perfectly. So we decided, okay, here we'll have to put old and new together again and use very traditional methods of mortaring bricks. But in the end, we liked it. And now, more recently, just in the last month or two, we're experimenting with a Delta bot that extrudes 3D printed clay. And we're working with Autodesk on a software which I believe they intend to ultimately be open source that allows us to not think so much about the form of the object, but to actually think about how we can program the machine to make design instead of designing the form itself. So we can take this line of clay for a walk and see what it does. So these new lines of clay remind me of knitted structures and sweaters, and I think they have the potential to have some insulative quality. Imagine scaling this up to a brick or a panel or a building. And again, we always like to look back to look forward. So instead of thinking about old technologies over here and new technologies over here, how can we use traditional materials but with new manufacturing methods? How can we look at and understand form and structure that takes advantage of those materials and continue to deploy that in smart ways as we continue to use them with these new manufacturing methods? So they are not two sides of a divide, but how can we bring those together? Paper. We often work with our students to develop new materials. This is a project by a student at the University of California who is interested in recycling newsprint into a 3D printable product. So he got his newspaper, he turned it into a pulp, pulverized it, and was able to develop a formula for 3D printing with it. Here you can see the resolution and the quality of that recycled newspaper 3D print. Wood. 7.1 million tons of wood waste is generated each year. We should be able to do something with that, right? And we can. So we've developed formulas for 3D printing with sawdust and agricultural byproducts. So this is 3D printed wood, and instead of subtracting, which is typically how we worked with wood, we're now adding. We're adding these small micron-sized particles of wood to make something new. And what's really interesting about the 3D printing with wood is that because 3D printing is a layering process, depending on the orientation of the object that you put in the printer, you get a kind of artificial grain, a new sort of 3D printed wood grain. And when printed thinly enough, the wood is also translucent. And we've printed with different types of wood. So this is a softwood, it's pine. This is maple. This is walnut. This is the sawdust screen made out of 3D printed walnut. And here, we have two different tiles that are repeated across the surface, but we use, in many cases, the Karakusa pattern to connect those tiles one to another so they always match up. And we were interested in creating different size openings that people would be able to look through and see framed views beyond. Rubber. This is a material that we've been working hard on the last year, and we're finally having some success with. In the United States alone, 290 million tires are scrapped every year. And 80% of those are currently recycled, but that still leaves 60 million tires a year that are going to landfill. So can we do something with this material? We have an industry partner that is taking this recycled rubber clump, and they're cryogenically breaking it up into a microfine powder that we're able to 3D print with. And one of the interesting things about the rubber, even though it's pulverized to the same size as the wood or the cement or the paper, each material has its own inherent properties. So when you 3D print something in wood, it comes out of the printer hard, but when you 3D print with rubber, it comes out of the printer pliable and a little bit spongy and soft. Plastic. So this isn't a material that we have invented, but we do work with companies such as MakerBot, and we are helping them develop examples or case studies for how end users might use their machines and their materials, this is PLA, to make things for architecture in the built environment. So this is a 3D printed block that we've printed out of their translucent orange, and we also 3D printed the connectors which hold the blocks together. So in this case, it's an opportunity for MakerBot to say, you don't have to make just little tiny robots, right? You can make architecture with these machines. And we also partnered with them to make this 3D printed dome, which is called the Star Lounge. The challenge here was to develop a structure that they could print, and we had to really think about file management. So for us, it's not an issue to say, oh, there's 1,000 unique files. Well, that's okay, we'll print them. We didn't want to send them what in the end was 2,500 unique files. So we worked really hard to develop a structure that would have a very small number of unique pieces. And in the end, I think there are only 27 unique hexagons that make up this structure, and they're color-coded, so all of the blue ones are the same, and the white ones are the same, and the orange ones were the same. And we made a little booklet for them so they would know how many to print of each one. So the piece, as you saw, is actually componentized. Oh, sorry, I won't make you watch it again. There are the 2,500 individual hexagons, but those hexagons are all riveted together to make these larger hexagons and stars. And that makes it transportable so that we can move it from site to site, and it can be erected in a matter of a few hours. Another thing to note is that it's incredibly lightweight. It weighs less than 200 pounds. The hardware weighs almost as much as the plastic does. Each of the hexagons is only 1.5 millimeters thick. So I think thinking about issues surrounding sustainability and how much it costs to transport things, how much time it takes to make things, there's an opportunity to have an impact here. Here's some views of the interior. So you can see the light coming in through the holes in the center of the hexagon, dappling the ground. And the PLA is translucent, so it's very beautiful and it glows when it's well lit. Salt. So you've all seen the salty glue. So this is a local material for us. It's a renewable resource. It's incredibly inexpensive. And when 3D printed and post-processed with our polymers, it's very strong. And one of the nice things about the salt is that it has beautiful optical properties. As you see in the exhibit, it's translucent. So it doesn't have to be printed as thinly as the wood or the cement. It can actually be a little bit thick and the light still passes through it in a really beautiful way. And we've experimented with different ways of interlocking and aggregating these salt blocks. This is a building designed by Tom Falders, and we 3D printed a salt model for him. This is a view of the crystallizers in the South Bay, owned by Cargill. And at one point, over 1.5 million tons of salt was excavated or was shipped from the bay each year. And it's not that much now because Cargill has sold 16,000 acres back to the government so that the land could be returned to its natural habitat. And they also set aside 1,400 acres that they would develop for 12,000 houses, about 30,000 people, which raised the question, could we build houses out of salt on this land? Again, can the material source and the building material itself be seamless? So we designed the salty glue that's made out of 336 or so salty tiles, which were inspired by salt crystals, the forms of salt crystals, the overall form of which was inspired by these very traditional baskets that were used in the salt extraction process to come up with the salty glue as a full-scale study model for thinking about architecture and salt in the South Bay. And here you can see, again, those really wonderful optical properties. And this is just from the natural light coming in through the window. There's not a light inside the salty glue itself. This was one of the first large projects that we built, and we were still in the early phases of thinking about how these tiles would connect one to another. So if you've been over to the exhibit, you probably see that they're binder clipped together. And we've moved on from that method of connection. But it was a really fast way to mock this up. So, as you're making things in your studio, I think you can be creative and use things that are on your desk to work with, right? And as we think about how this could become architecture, we developed a house for a developer in China, I should say a schematic design for a house, for a developer in China who wanted to use 3D printing at a resort called Jinhai Lake. And we proposed these 3D printed salt interiors that would be the more private spaces of the house, like bedrooms or offices, and a 3D printed cement exterior of the house, which again would be made out of cement blocks. And I guess we think about this or approach this a little bit differently than what's being done in China, because we don't see that 3D printing has to be one big gesture, right? You don't have to print the whole house in one shot. You can use different materials. And the buildings and the spaces that we live in and work in now are made out of many different materials. And components are the size that they are so that we can carry them and we can work with them. A brick fits perfectly in your hand, right? A nail is the size of your finger. So going forward, I don't think that we have to 3D print a giant house in one shot out of one material, but we can print components, and those components can be integrated with traditional materials. And this is a prototype of what that 3D printed cement facade would look like. And cement. So cement is the most ubiquitous building material in the world. And we have developed 3D printed cement. We've transformed it for the 21st century and for use in additive manufacturing. We've patented this process and we've tested it. Our cement has a compressive strength of 4,700 psi. You probably know from your structures class that cement at 28 days or concrete at 28 days is only 3,000 psi. So our 3D printed cement is actually stronger than traditional concrete. And it's translucent. We've experimented with different ways of finishing the cement. So here, for example, it's sandblasted so that it could be matte. We've experimented with different ways of connecting panels to make larger structures. This is Andrew Cutlass's P-ball. So here you can see all of the unique 3D printed parts come together perfectly, absolutely perfectly. And finally, another project at Fort Mason as kind of a proof of concept to show that the cement material is really commercially ready and viable. We designed a cement project called the seat slug, the form of which was inspired by the most recent species of sea slug discovered off the coast of California. And this is kind of our workflow, it's our process, you're probably familiar with it. Here we designed the base surface for seating. So it's 11 feet long and it's about 16 inches high, which is the right height for a lounge seat. And we thought about how we would deal with structure, so it's designed to be a series of arches. And then we distribute points along that surface, which you can see in these two models. And then we give those points depth, because we have to have panels or tiles or blocks that have depth so we can connect them together, right? And we do that with the floating point grid. And we further subdivide those points so that they fit within the build bed of the 3D printer. When we design a tile, we use the Karakusa method of tiling so that as that tile is repeated and rotated, they always match up, but you don't get a repeated pattern that's legible. And those tiles are then in Rhino panelized across that point distribution, which you saw in the previous slide. Here are all the 3D printed cement tiles laid out. And this is a rendering of the seat slug. It's not the actual seat slug, but it's important to show because the actual seat slug comes together with the exact precision shown in the rendering itself. And these are the 3D printed cement tiles, and you can see that everyone really is unique. They're all different. Here you see the depth, that offset from the point distribution, and we printed the holes in each tile so that we could mechanically fasten them together. We post-process all of our materials to give them strength. And there's the final seat slug. And more recently, we completed a project called Bloom, which is also made out of 3D printed cement. It's a tempietto, it's a celebration of 3D printing, and we did this in conjunction with a cement company called SCG in Thailand. They're the 6th largest cement company in the world, and they wanted us to develop their material for 3D printing. So this was one of the first times we've taken someone else's material and developed a formula for it, because they are interested in commercializing 3D printed concrete building components and selling them in Asia. So the Bloom, as we call it, is made out of 880 unique 3D printed cement parts. And the cement is white, unlike our cement. It's an iron oxide-free cement. And it has a flower pattern cylindrically mapped onto the geometry of the tempietto, which is what makes each tile unique, because you see the bottom and the top half are the same formally, but rotated 45 degrees. But the flower pattern is what gives it uniqueness across the surface. And the flower pattern also allows for openings and light to pass through in really interesting and beautiful ways. Here you can see the 3D printed blocks themselves. And again, we 3D printed in the holes. Each piece is numerically coded, and the blocks at the bottom are 4 inches deep, and the blocks at the top are only 1 inch deep. So as you go up, the blocks get thinner and smaller and lighter. So here you can see the plan and how it is actually symmetrical from side to side, and how the top is the same as the bottom but rotated on that 45-degree angle for structural integrity, because unlike the salty glue, there's no secondary support system. This is the interior. So from the interior, you don't read the leaf pattern quite as much, but you do see the structural grid. So each block that you see here is divided into 4 quadrants, and there's a structural grid or a cross inside each block, which gives it additional strength. And here's the new and the old together. So the 3D printed cement block of Bloom next to Worcester Hall at Berkeley. And we had to think about portability, because this project is going to live in Thailand. So how could it be taken down and put back up with ease? How could it be shipped to Thailand? So we left each of the blocks connected into 4-foot by 4-foot panels that could be carried by one person and then assembled quickly on site. And again, looking back to look forward, in thinking about the design for the form of this, we were inspired by the Indabelli people and the forms that they used and the types of openings in their houses and the geometric patterns on the surface of their building. And one last project, Sol Grotto. This is a project that takes advantage of a material that I like to think of as neo-vernacular to the Bay Area. This project uses glass rods that were designed and engineered by Solyndra. Solyndra is a company that developed a solar tube that would ideally replace a solar panel. And the way it works is that there are 2 glass tubes, a 1/2 inch diameter one on the interior and a 3/4 inch diameter one on the exterior. And in between that is a thin solar film. And this tube could collect light from all different angles and reflected light from the roof and generate energy, so it didn't have to track the sun. But as you probably know, Solyndra went bankrupt.
Good evening, I'm Ken Baskito.
I'm Dana King. Tonight, a CBS 5 exclusive. Remember Solyndra, the failed solar company in Fremont?
Solyndra still owes American taxpayers $500 million, but we caught them destroying millions of dollars worth of parts. Elizabeth Cook with the video you'll see only on CBS 5.
Well, Solyndra will put its assets up for sale again next month, at least the assets they haven't yet destroyed. Look at what we found last week. At Solyndra's sprawling complex in Fremont, workers in white jumpsuits unwrap brand new glass tubes used in solar panels. They are the latest, most cutting-edge solar technology, and they're being tossed into dumpsters.
So they got busted, and they had to stop throwing away their assets. And they put out a call around the West Coast to artists and designers and invited anyone who wanted to come pick up the glass rods. So I drive by this company on my way to teach every day. So I stopped in and picked up some glass rods. And we decided these rods had a lot of potential and they were very beautiful and that we would be able to use them in a project at the Berkeley Botanical Gardens that we were designing for an exhibit called Natural Discourse, where artists and architects were asked to look at the relationship between the garden and the environment and the visitors. And so we built the Soul Grotto, which is inside this little wooden structure in the Botanical Gardens right in front of Strawberry Creek. And when you walk inside the Soul Grotto, you're greeted by 1,400 of the Solyndra tubes, which are naturally glowing by the sunlight. And they glow this beautiful electric blue, even on a foggy, dimly lit day. And the form that the tubes take is reminiscent of a kind of rocky surface that you might find in a traditional Italian grotto. And because the tubes are hollow, the cool air from the Strawberry Canyon Creek behind it blows through the interior of the rods into the space. So making what was once a hot, sunny place to sit, a nice, cool, quiet place to sit in the garden. And some interesting things happened when we first installed all of the glass rods. Thousands of ladybugs came to live on the glass rods the first week. And they left, and then each rod became a home to a spider or a mosquito. And we really loved the way that the garden started to weave through the glass rods and take over the Soul Grotto. We liked the way light reflected and refracted through the glass rods. And we liked the way people interacted with the glass rods. If you look closely here, you can see how the exterior started to change. Because of the water from Strawberry Canyon Creek, algae started to grow in the glass rods, and from the exterior they started to glow green instead of blue. Views from the outside looking in and the inside looking out. And a view of the Soul Grotto in the fairly quiet Berkeley Botanical Gardens. So after the opening of the Natural Discourse exhibit, somehow Fox News found out about this project. And this is not how I imagined my national debut as an architect would go down, but this is what happened. They called us and said, hey, we're going to talk about the Soul Grotto tonight. Send us a picture.
Welcome back. So finally, someone found a use for Solyndra, taking 1,400 glass tubes recovered from that boondoggle and fashioning it into an art exhibit at the Berkeley Botanical Gardens. Lovely. As you know, Solyndra went bankrupt, laying off all its workers with $500 million in taxpayer dough dissipating in a cloud of dust. So now our loss is someone's hip, pretentious art, which makes sense. Most modern art and alternative energies are a lot alike in that it's up to the believer to find value in it, because for the rest of us, there is none. Both function as a platform for phony intellectualism, and the only energy generated comes from goofy bureaucrats drunk on our cash, driven by a need for acceptance by the cool green crowd. Meanwhile, when it comes to real stuff that works, like nuclear power and fracking, greenies would rather create panic than actual energy. Well, you know what? We paid for that art, so we should all get a piece. We could take a sledgehammer to it and call it performance art and charge admittance. I'm kidding, of course, that would be wrong. But since the exhibit is kind of boring, I decided to sketch an alternative. I added a unicorn for obvious reasons. Now, if you contact me and give me the name of a relative who needs some cheering up, I will mail it to him or her myself. That way, Solyndra will have done some good, even if it's unintentional.
So So we asked him to send us that picture, but he never did. But anyway, after Fox News ran this story, there was a media rush on the Berkeley Botanical Gardens, and everyone came to see the Soul Grotto. So ABC, NBC, CBS, NPR, and there started to be a discourse around the use of this material in the building at the Botanical Gardens, and again brought up the conflicting nature of investment in technology itself in the Bay Area. Chairman of the House Energy and Commerce Committee, Fred Upton, said, "To date, the most expensive piece of art ever sold is Paul Cézanne's The Card Players, which the country of Qatar bought for $250 million in 2011 from the late Greek shipping magnate George Imbrikos. With a price tag of $500 million and just $24 million expected to be repaid, the amount taxpayers forked over with little to see in return except the Soul Grotto would make this piece of art shatter that previous record." And because of the Soul Grotto, House members approved the No More Solyndras Act and a 245 to 161 vote, which would curtail the Department of Energy Loan Guarantee Program that backed the $535 million federal loan to Solyndra. The Senate did not pass this bill, which is a good thing.
If a political discourse has by itself brought people into the garden, then I would say finally politics has done something useful for us.
So I think Paul Licht, the director of the Botanical Gardens, summed it up best when he said that. So what does it mean to use these materials that are politically charged, that have a social and environmental consequences? And how can we take advantage of that through the creation of the built environment in order to have a more meaningful conversation around social, political, environmental issues in the built environment today? Thank you.